Well, welcome to this overview of machine learning in Microsoft Excel. I only finished this this morning. Um, well, 2 o'clock in the morning. I'm really excited about it and actually working. But before we start, I'd just like to say that humans have 86 billion neurons. Blue whale, about 30 billion. A bee, 1 million. An ant, 250,000 neurons. A worm, 302. And what we're talking about here in this little spreadsheet is just 2 neurons. But before we get all high and mighty and thinking, look how many billion neurons a human brain is, I'd just like you to look at that last item on the list. An elephant has got 3 times as many neurons as we have. I think that's a salutary point. Anyway, let's move on. So what are we trying to do? We are trying a very first attempt at generating the sine from the angle given in degrees. So we're taking an angle in degrees, like 45 degrees. We are converting it to radians because Excel works easier with radians. And then we are using, I did say 2 neurons, actually it's 4 neurons. But anyway, not very many. 4 neurons to determine what is the sine. The sine of 45 is 0.7071, I don't know, something like that. So we will train it on those, and then we will give it another angles, a random sample, and see how accurate it determines what the sine of that angle is. Right, let's go on with it. Let's get to the output first. So this is the total spreadsheet. There are 1, 2, 3, 4, 5 basic areas here. And rather than go through each one now, let's just talk about a quick overview of them. This is the data input data points. There's 5 data input points there. It's a sine wave we're using. These are data values for the hidden layer. We'll come back to that in a minute. This is the accuracy figure. It continually revises accuracy, and we drive the accuracy as accurate as possible, which drives these figures up to update themselves. These are the test data points done here. So we've got input draining points and test data points. We don't use them, don't mix them up. We have weights and measures, weights and bias in the hidden layers. Why are they hidden? Well, they don't mean much to us, but they need a lot in calculations. We have a structure of the neural network. We'll come on to that too. And then the output chart. Let's have a quick look at the output chart first, so you can see what we're looking at. And there we are. So this is the red response. This is the accurate response from the trig functions. We know that's absolutely right. And this is the learning, the blue one. We're 20% out or so at the end, which is significant error. But we can improve that. These are our training points in degrees, in radians, and these are the hidden layers data, outputs, and that's the accuracy. Let us have a quick look at going through one training loop. We go into data, and we scroll across onto solve, and this window comes up, and we want to minimize this value. And how do we minimize that? We can change all these weights and biases, and that's what we put there. So that's all we have to do. We don't want maximize, we want to minimize the weights, and then we click solve. Non-linear, uncontrolled, yes, so click those buttons, and then we come to solve. But before I solve it, let's have a look at the graph and click go. Look at that. Our first run around the loop, and we have got tiny bits of errors at the beginning. Let's click on that. Do you want to save that? Yeah. So it's dramatically improved, and the error has reduced dramatically to 3588. Let's go through that loop once again up to the solver and see if it changes. And what was it, 3588? Let's give it a go. There we are. It's improved by a factor of almost 10. Let's keep that. So every time we go through the loop, it gets better. Right. But I'm going too deep. Let's have a look at the neural network itself. We have input, we have output, we have the hidden layers, one hidden layer, two hidden layers. We have two neurons, neuron 1 and neuron 2. Compared with an elephant, not very many, but never mind. And then we have the output. These are the biases, hence the B, and the W are the weights. Right. How do we work through this? It's quite straightforward. Forward pass is quite straightforward anyway. So this is the input. Let's say it's 30 degrees. We take that input value, we multiply it by a weight to get the value in N1H1. This N1H1, this 1 value, is quite simple, 2 multiplications. Oh, time the bias, minus the bias. So that's a little subtraction there. Once we've got that value, how do we get this value of 1, 2? Easy. We get this value and multiply it by W3 to get that, not forgetting we have an input from this neuron as well. So we take this value, multiply it by W4 and add the two together. And it's the same with here. Take this input times W2 to get that value, 221 rather, this 21 value. Then to get 22 value, we multiply this value by W6 and add it to 11 value times W4 to get 22. So now we've got these. Then how do we get the output? Well, take a guess. We take this 21 value, multiply it by W7 and add it to this value 22 times W3. And then we apply the bias. And that is all there is to it. In the forward pass, that is all there is to it. Really simple, and Excel eats it up. Right, then we start to get the back process, which is chain rule partial differentiation. Not to worry, once again Excel does it for us in its solver. Fantastic little thing in is Excel. Right, let us go down to sheet 2 and have a look at some of these equations here. So N1H2 is there. So we take a sigmoid. A sigmoid is the only bit of code really which we have to put in, which is that, type that in exactly as it is into developer Visual Basic solver, and then we just come back here and we just say sigmoid, and that limits the values here to 0 to +1. Rather like the nerves do, we don't get very, very high potentials in the nerves, so it's restricted. It's a restricted value. Right, so these are the training, this is the training data, and now we're looking at the test data, and these are the charts. Really, that is it. Yeah, let's go into here. How do we calculate N1 H1, well, we do that. If you click in there, you can see we multiply the input and we use the weight 1 and the bias 1. The bias 1 applies to everything above it, and the same way as this, the bias will apply to everything above it. So it's quite a straightforward calculation. Okay, so let's not go into the formula. They're quite straightforward. As I said, to get N1 H1, H1 N1, we take the input, multiply it by W1, the weighting 1, and subtract the bias. Same for N2 H1, 2 1 there, and for 1 2 here we take that input, multiply it by W3 plus that input multiplied by W4, subtract the bias, and it's the sigmoid of that combination. And finally the output is simply 1 2 multiplied by W7 and plus 2 2 times W8 minus B3, and there's B3, and it doesn't matter what you put these to. Just remember, it doesn't matter what, you can put random numbers. In fact, you do put random numbers in to start with. Make it up. It doesn't matter, because whatever you use in here, it will pop out here and it will show rubbish. Let's do it. Right, that's the screen now. It's quite nice and tight. Bit of error on the beginning and a bit of error on the end. But let's make W1, I mean, okay, it doesn't have to be much. Let's put it as to a 1. Okay, doesn't matter what it is. And now look what's happened. It comes adrift. Let's put, let's make W6 1 as well. And there we are, variance again. And all we have to do is to run data analog to solver, and click solve, and that starts to come back into place, and we just do that a few times and it gets better. Yeah, look at the error now, tiny. Okay, so we've had a quick look then. This is the 2 neural network in the hidden layer, and the error, I just got into the formula there, I just realised I hadn't shown you that, is the difference between a matrix sum. Yeah, actually it's a good point, actually. Sum matrix of those two fields, matrices, and that squared. It gives you a rough idea of how to do machine learning in Microsoft Excel with 2 neurons. I'll just leave you with one thought. I think you know what it's going to be. Look at that elephant.